All right, we made it to chapter 5, and this chapter is going to be looking at probabilities in terms of graphs. And the fancy name is called a continuous random variable. And we're going to be looking at something called a continuous probability function. And to do that, here are some different graphs, and these are all graphs of different probability situations. And these are called distributions. First one's a uniform distribution. That's going to be a consistent probability between a range of values. So this would be something like rolling a singular die and having equal chances for all the different outcomes. The normal distribution is something we're going to be looking at in a lot of these chapters. And that's going to be something that's centered around a point in the middle of the most common outcome, and then it tails off on both ends, such as the weight of humans. That counts as that would be a normal distribution when everything is centered around an average, and then we have outliers and lower percentages as the further we get away from the mean. And then we have an exponential distribution where it starts off with a very high probability and then it levels off going to next to nothing. The shaded region is what we're going to be looking at. That's going to give us our probabilities. This video is looking at uniform distributions, and uniform distributions are going to be calculating this, the rectangle. So very straightforward at first. So here is an example of a continuous probability density function, and we use the f of x notation. And notice the probability here. The maximum probability is 1, so the area of this whole rectangle will be 1. And we're going to calculate the area inside of a shaded region. That's going to be called our probability area. All right, so this is known as, or here are some properties. We're going to be once again calculating the area under the curve. And let's move forward. So everything here is measured. And we have some properties here. I think the properties, you can go ahead and read these if you want, but they're best shown by looking at some examples. All right, so here we have an example. This is going between 0 and 20, which we can notice by the x-axis going from 0 to 20. This would maybe be like rolling a 20-sided die. Each outcome has a 1 in 20 chance of happening. So it's a 1 in 20 here for the probability. And what makes these unique is this is going to be where we don't necessarily just locate just we don't find the chance of rolling like a 17, because there could be decimals in here too, 17.2, 17.3. So it's a continuous probability function. If it was rolling as a 20-sided die, there'd be 20 little dots up top, and there wouldn't be all the decimals in between. So here we go. We can see the function equals 1 over 20 for x between 0 and 20. It's a horizontal line. The area between the function and 0 to 20 is a rectangle with a base of 20 and a height of 1 over 20. And if we take base times height, we get 1. There we go. So for example, if we want to find the area between the function and the x-axis, where x is between 0 and 2, what we would do is shade that on our rectangle. So between 0 and 2, up to 1/20th, we recognize that's a rectangle, and we simply calculate the base and the height. The base is the distance between 0 and 2, so 2 minus 0, multiplied by the height. So 2 multiplied by 1/20th, 2/20ths, or 1/10. So 0.1, 10% chance of happening. Here's the work showing that. So we would write this out. The probability as x is between 0 and 2 also is congruent to the probability of, or equal to, the probability of x is less than 2 would be 0.1. We have other problems, very similar. Between 4 and 15, you calculate that area, or that length, 11. 11 multiplied by 1/20th, 0.55. If we want to find x equaling 15, it's not very possible because if we think, or I guess it doesn't really make any sense because that would be just a vertical line with no width. And if we have no width, we can't find the area of that rectangle. So technically here, the probability x equals 15 would be 0 because there would be 15.0001 right next to it. There are all of the decimals. So we need to have a range of values on these continuous probability functions. So we're going to be using inequalities a lot. Okay. Down here, they talk a little bit about what this CDF stands for. Cumulative distribution function, CDF, stands for less than or equal to. We'll talk a little bit about that. So that'd be the area to the left of something. So we're going to be looking at that in a little bit. All right, so probability of x less than or equal to x. So when we're going to the left of something, we also written as x is less than or x because the equal to part doesn't change anything. It's called the cumulative distribution function, the CDF. So notice it's going to be less than or equal to. So that's just main part here is it's always showing us to the area to the left of it. So here's another example. Same function or different function, f of x equals 1/8 from 0 to 8. Draw the graph from 2.5 to 7.5. So we find 2.5, we find 7.5, we shade that in, then we calculate that area. Difference from 2.5 to 7.5 is 5. 5 multiplied by 1/8 is 0.625. We'll talk more about that CDF in just a moment. So we're going to be looking at the uniform distribution function, the exponential, the normal distribution. Here are, once again, examples of those three. So we didn't really get too much into this, what this CDF means. We'll talk more about that in the coming chapters, but just remember to find the area of these shapes. For our simple ones, we take the area of the rectangle. That's what this first lesson is about. In our next lessons, we'll get a little more complicated. All right, thanks. Bye.